In this video, we discuss the situation with counters that have unused states. To the counters that are 2 to the power n. We know that a circuit that has n flip-flops, it has 2 to the power n states, which means if there are 3 flip-flops, we have 8 states, 4 flip-flops, 16 states, and so on. Often we design the counters to include 8 or 16 states, etc. However, sometimes we may have to design a counter with a given sequence, which means it does not count 0, 1, 2, 3, 4, 5, 6, 7, etc. It counts differently. And in this case, there may be states that are not used. We will give an example soon. Now, the unused states can be treated as don't care conditions or assign a specific next state. If we use them as don't care conditions, it will make the design of the combinational part easier. Now, an outside noise, it may cause the counter to enter to one of the unused states. If that happens, we must ensure that the counter eventually goes to the valid state. We can't accept that the counter stays in an unused state because the counter will not be used otherwise. Let's take an example. Suppose we would like to design a counter that counts repetitively the sequence 0, 1, 2, 4, 5, 6. And we want to do this using JK flip-flops. Of course, in this sequence, we notice that there are 2 states that are not used, which are 3 here and 7, because the counter will count 0, 1, 2, 4, 5, 6, 0, etc., etc. In order to complete the design, we need to prepare the state table and then to derive the flip-flop input equations. The state table is as follows: the present state and the next state. State 0 goes to 1, 1 goes to 2. We follow this sequence up here that we have just mentioned. And state 2 will go to state 4, 4 goes to 5, 5 goes to 6, and 6 goes to 0, and so on. To derive the flip-flop input equations, first we need to find out the values of the J and K for the 3 flip-flops, which are A, B, and C. We find them as we described earlier. We look at the present state of A and the next state of A and determine the values of JA and KA. Same thing goes to all states of A, present and next, and also to the present and next of B and C. We find the values as we can see in this table here. And please verify these values. Take your time in order to derive the values of JA, KA, JB, KB, JC, KC. It is very important to understand the process. We find out Carnot maps to each of the J and K of the flip-flops, and then draw the logic diagram, which we see here in this diagram. So flip-flop A, the inputs J is equal to B, and K is also equal to B, and the flip-flop B, the J is equal to C, and the K is equal to logic 1. That's what we find from the previous values of J and K. And finally, flip-flop C, J equals to B prime, and K is equal to logic 1. Now, the state diagram of the counter, as we can see here, it goes from 0 to 1, 1 to 2, 2 to 4, 4 to 5, 5 to 6, and 6 to 0. Now, the question will be, what happens if the flip-flops go to state 3? State 3 means A is 0, B is 1, and C is 1, because A is the most significant and C is the least significant. So if that happens, what will be the next state? I think the only way we find out is really to analyze the circuit in detail. So if that happens, we will find that J and K of flip-flop A will be 1 and 1 because B is equal to 1, and J of B will be also 1 because C is equal to 1, and finally, if B is 1, B prime is 0, and therefore J here will be 0 and K is equal to 1. Now what happens at the clock pulse? Look, for flip-flop A, J and K are both 1s. Therefore, this flip-flop will toggle, which means this will be 1. And for a flip-flop B, also J and K are 1s, which means it will toggle, it will complement, so this will be 0. And finally, a flip-flop C, J is 0 and K is 1. It means that C will be cleared, and this will be 0. So we can conclude that if we are in state 0, 1, 1, the next state will be 1, 0, 0. And in the state diagram, we can write this state 3 here will go to 4. Same thing exactly. We can also analyze what will happen if the counter goes to state 7, which means if the counter is 1, let us now change all of this. If A is 1 and B is 1 and C is 1, that's state 7. What will be the next state? Again, we need to analyze the counter in detail. When B is 1, we find J and K of a flip-flop A will be 1s, and also J and K of flip-flop B will be 1s, and J of C will be 0, and K of C will be 0. Therefore, what happens is the first flip-flop A, J and K are both 1s, it will complement at the clock pulse, so this will go to 0 here. And the flip-flop B, also J and K are 1s, so it will complement, so this will be 0 here. And finally, a flip-flop C, J is 0 and K is 1, so it must be cleared, and 0 will be here. Therefore, if we are in state 1, 1, 1, the counter will go to state 0, 0, 0, and this is how we represent it on the state diagram. Now, to summarize again what we have done, we are asked to design a counter that goes through the states 0, 1, 2, 4, 5, and 6. We designed the counter and draw the logic diagram, and it was as in this circuit here. And then the unused states, which are 3 and 7, we take them one by one and we analyze to find out what will be the next states, and we found out, luckily, that the next states are states in the sequence that the counter goes through. Now let us give a hypothetical case. Suppose that if we are in state 3, the counter stays in state 3. It doesn't go here. And if we are in state 7, the counter either stays in state 7 or goes to state 3 here. Would this counter be useful? No, it will not be useful. Because if it is by mistake or by noise, the counter goes to any of these two unused states and stays in one or two unused states, the counter will never go back to these states, and the counter is not useful. We must change the design. We can change the design by revising the previous state table by writing 0, 1, 1 as a present state, and we can write any other of the 6 used states here in order to correct our design.